So we're going to have a look at this example for collisions with two walls here, and let's just read through and see if we can pick out any of the things that we think are most important. So two cushions on a snooker table, W1 and W2 meet at right angles. Well, it would be a very odd snooker table if they weren't at right angles. A snooker ball travels across the table and collides with W1 and then W2 in that order. The cushions are modelled as smooth. Just before the first impact, the ball is moving with speed u meters per second at an angle of 20 degrees to wall 1. The coefficients of restitution between the ball and the cushions, wall 1 and wall 2, are 1/2 and 2/5 respectively. So they've got a different coefficient of restitution. That doesn't really seem to be very realistic, does it? Why would a snooker table have different coefficients of restitution for different sides? That's not really how you design a snooker table. But whatever, they've told us that's what it is. So it wants us to find the percentage of the ball's original kinetic energy that is lost in the collisions. And then it says something, in reality the cushions may not be smooth. What effect will the model have had on the calculation of the percentage of kinetic energy remaining? So we'll come and think about that one in just a second. Okay, so we've got these two things that are going to be at right angles. So we know there's going to be a double collision that looks like this. And it says, first of all, it is moving in at a speed of u at an angle of 20 degrees to the cushion. Then we know it's going to bounce off somewhere like this, and then we know it's going to bounce off somewhere like this. Okay? Let's call this wall 1. Let's call this wall 2. Right, what I prefer to do when I do these questions is I prefer to do the first collision completely separately with its own diagram, and then the second collision afterwards. So for the first collision, we have u coming down, and that's 20 degrees. So running along the bottom is u cos 20 running along the bottom, and then coming down here is u sine 20. Now, you can do the next bit with a v and an unknown angle, or you can do what we've started doing in some of the previous lessons of almost going straight onto the diagram with some new values. So we know it's going to be bouncing off like this. What's the value running along the bottom going to be? It's also going to be a u cos 20, and the value going upwards would be what? Good, because the coefficient of restitution here is that e is equal to 1/2, so it's just 1/2 u sine 20. That's because the first collision is equal to this. So what kinds of information do we need to find out for this second triangle that we've got here? So we need to find the hypotenuse, and we need to find the angle. So if I call that angle theta, we know that this is 1/2 u sine 20, and this is cos 20, u cos 20, sorry. So we'll find out what the speed v is. So we know that v squared equals u squared cos squared 20 plus this squared, which is 1/4 u squared sine squared 20. So we could factorize that right-hand side, and you get u squared cos squared 20 plus 1/4 sine squared 20. So v is equal to u, the square root of this, which I think we probably just want to work out on a calculator. So let's work out what the square root of that is. So I've got that v is equal to 0.9551265 blah 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 u, from just inputting that bit onto the calculator there. That seems quite reasonable, that it's lost some of its overall speed. Okay, so the other thing that we said we wanted to do was to find out the size of theta. How am I going to find out the size of theta from here? Good, so theta is the tan inverse of what over what? Opposite over adjacent. So the u's are going to cancel, so it's a half sine 20 over cos 20. So theta is equal to, let's work that out, so that's the inverse tan of a half sine 20 over cos 20. And we get that the angle is 10.31410. I've just written a few numbers out. Why do you think I've written a few numbers out?
So you get more accurate.
Because you might need to use it later.
Yeah, because I'm probably going to need to use it later on. So now that we've got that second part of it done, we can draw for our second collision, which I'll do over here. I go back to this diagram and probably want to add on the fact that that's a right angle. That's our 10.31 degrees. So we're now going to think about that second collision that we have. We know that it's going to be coming in at quite a severe angle, and we can work out this angle, which is this one up here. Yeah, it's going to be, let's work that out, so it's going to be 90 minus that. So it's 79.6858, keeping that quite rounded. And we know that the speed that it's coming in at is 0.9551 u. So they just start getting a bit more complicated, and it's where we need to keep ourselves really organized with our diagrams. So we have this and this. When it bounces off, we're going to have this and this. This is where things start getting a bit messy because there's quite a lot of numbers that need to be written on here. What's this one going to be along here? The sine or the cos? It's the sine. So it's 0.9551 u sine of, I'm just going to put it as 79.69 for now, that's probably enough. And then along here, it's 0.9551 u sine, not sine, cos of 79.69. Now we know this one is also going to be that as well, 0.9551 u cos of 79.69. And then this one that we have over here, what would that one be? Yeah, and what's E now? Yeah, E in this place is 2/5. 2/5, I'm just probably going to take this to a decimal just because everything seems to be in a decimal so far. So this bit up here is going to be 0.4 times 0.9551 u sine of 79.69. So, which of these things am I interested in for this second triangle that I've got over here, for this purple triangle that I'm going to draw on? Am I interested in the angle, which I'm going to call alpha, or am I interested in this bit, which I'm going to call W? I'm interested in W, because W is going to be the speed, and remind ourselves of what the question wanted to look about. It wanted to think about the kinetic energy that's being lost in the collisions. So we're going to just try and find out what W is. Now we're going to look at Pythagoras here. So we know that W squared is equal to this squared plus this squared. Yeah, I'm going to actually just factorize out the u squared straight away. So it's going to be u squared and then this thing here squared, which is going to be 0.955 cos of 79.69 squared plus 0.4 times 0.955. Because they've got, both of them have got a u in. 0.9551 sine of 79.69, and all of that is squared. Now I'm not very good at using that stored bit in the calculator. So should we try that? So what do? I just press
the arrow. So press the arrow, it should say answer arrow.
Answer, arrow.
And then alpha.
You have to press alpha first.
Yeah.
Okay.
And then execute.
So we can now work out this thing. So we're nearly there with it actually. We probably didn't need to be quite as organised with that. I'm going to keep it as w squared. Any idea why I'm going to keep it as w squared rather than as w?
Because E equals half
Yeah, because the kinetic energy is going to be using the speed squared. So this is quite a lot of calculating we're going to need to do here. So I've got 0.955 1 cos A all squared plus 0.4 times 0.9551 sine of A all squared. So I believe you get that W squared is 0.1705 ... U squared. So I think that's right. I might even need to look. What did we get in? Let's see what it is in this book, just to see we've got it.
But the book will only give you the answer straight.
It's all right.
It's an example. So
I've taken it from one of these. Yes, it is the right number. Okay, so that is the speed that it has at the end. Now we just need to make a comparison about the two speeds. So this is the thing I actually think can be quite confusing. It says here, find the percentage of the ball's original kinetic energy that is lost in the collisions.
So it's lost over
Half
original
M.
and
So it's the lost over
the original
the original. So the amount.
as a percentage.
So it's
So-
half m u squared take away half m w squared.
So yeah, the amount that is lost is a half m u squared minus a half m w squared, and the original is just a half m u squared. So when we put that all together, you will get a half m u squared minus a half m w squared all over a half m u squared. We can cancel out the halves and the m's, so it just ends up as being u squared minus w squared over u squared, which is u squared minus 0.1075 u squared all over u squared.
Now the u squared.
And now the u squareds will cancel out, so you get 1 minus 0.1705. And we probably could have just sort of thought about that sensibly rather than having to do that, but I quite like having the formula. So if we just do 1 minus that answer, we get 0.82948, which is 82.9%.
Part A.
And that's part A.
Part B is no, that's part B. Part B is really short.
No,
Part B is really short.
Plus 1
Oh,
there.
wow.
Part B said, what would be different? Let's just remind ourselves of what it said. It said, what would be different? In reality, the cushions may not be smooth. What effect will the model have had on the calculation of the percentage of kinetic energy remaining?
Would there be less remaining?
There will be less remaining. Good. So for part B, if not smooth,
Percentage loss of one.
yeah, the percentage lost would be larger as energy is lost due to friction. It's just long, isn't it? There's nothing hard in this. It's just really, really long for that kind of thing that we've got there.
Is that mine? Is it mine?
The other way that we could have thought about this bit is we could have just thought from this stage here, we didn't really need to do all of this work. We could have just seen that the speed that it has at the end, the w squared, is 17% of the speed that it had at the beginning. So the amount that has been lost would be 100% minus 17%. But I just think it's useful to make sure we're setting things up in case it was asked in a slightly more confusing kind of way. Okay, so this one's fine. This one I just think is an application of everything we've done so far. This one is a little bit different. Let's just read through and see if we can figure out why this one here is different, and then you're going to do some questions for me. So this time, we've got two smooth vertical walls. Remember when we've talked about vertical walls, we're not meaning vertical, we're meaning bird's eye view. Stand on a smooth horizontal surface, and they intersect at an angle of 60 degrees. So there's the thing that's different. This time, the walls are not at right angles. This time, they are like this. They're kind of like kind of weird corners. And we don't really come across walls that are like this unless you're in like I don't know, big university buildings or libraries where they have weird architecture. Normally we just have right angles for walls, but this time we've got a particular situation that's like this. All we need to do differently here is be very careful about the diagrams that we draw and solving the angle problems. So again, we've got a smooth sphere. It's being projected across the surface with speed 1. Thank goodness, 1 is nice and easy, at an angle of 20 degrees to one of the walls and towards the intersection of the walls. So all that's really saying is, here's the kind of setup that we've got where it's 60, and it's being at 20 degrees to one of the walls. Generally, it's going to be easier to think of all our problems kind of coming in from the left and bouncing around these walls like this. So what we can predict is happening is it's coming along here. Here's the path of the ball at 20 degrees. It's then going to bounce off somehow, and then it's going to do some more bouncing like this afterwards. So this is the pathway that the ball is following. What do you think the strategy is going to be able to work out its speed and direction across this whole journey?
Wouldn't be the same thing, just instead of having the angle as 90 minus that,
Yeah.
it would be 180 degrees, 60
Yeah.
degrees.
So it's nothing that different. This bit over here, we just need to be careful about how we find that angle, which I'll do in blue here. So let's just do it really quick, shall we? Let's do our first collision. This first diagram that you have here is always really important for helping you reason what's going on. I like the second diagrams to try and make it a bit more simple. So we've got that it's coming in like this. We know it's 1. So if that angle is 20, that one is going to be sine 20. That one is going to be cos 20, which means when it bounces off, it's going to be cos 20, and going up, it's going to be e sine 20. Has it told us that? Yes. It's told us that the coefficient of restitution for both of them is 0.4. So going up is 0.4 sine 20. Then I would recommend drawing that triangle out again separately here. So we have 0.4 sine 20 and cos 20, and I want to find out v. So v squared is cos squared 20 plus 0.4 sine 20 squared. So we can find out what v is. Let's do that on our calculators. So square rooting the answer, we should get that v is equal to 0.4945992134. Just keeping it nice and long. So I'm going to now store that. What do I do? The arrow button, and this time I'll put it in A. Okay, good. So we've stored that in A. I'm just going to remind myself I've stored that in A here. Okay, I've stored that in A. So now we just want to go back and find out what the angle is as well. So let's call this angle here alpha. Alpha is found by doing the inverse tan of 0.4 sine 20 over cos 20. So that is the inverse tan of good. So 8.28 degrees. I'm going to store that in my calculator in B. And now we can say that this is the one that's roughly 8 degrees. So if this is 8 degrees, we now just need to think carefully what this one will be. So it's 120, take away 8, which is 112. Yeah, that's right.
8.28 something. Or does it tell us around it?
No, I just rounded it to 8 roughly, so maybe we shouldn't do it as 112. Maybe instead we should actually do
111.716.
so it's 111.71. 111.716.
That's a lot smaller than 112.
So yeah, it's dramatically different. So now we'll just do our second collision. And this is where I kind of imagine my whole head like rotating around to see what this looks like. That's very odd that it's coming in at that angle.
Yeah, because it's not coming up as steep as you drew it. It's
Yeah.
coming up really shallow.
I just want to see that we've done that one right. Yeah,
It
so
should
it's,
have been
so actually this diagram is wrong because this is 111. So actually why
when it
don't
comes really shallow, it'll be really steep on
So actually it's going like this, then it's going like this, and now it's going to bounce like this. So that ended up as being 8, which meant that was whole thing was 111. So actually this diagram is now the new one we're going to use. Instead of it being 111 here, we actually have to do 180 take away that, which is 68.28. So actually now it's a 68.28. Because of the fact that it was greater than 90 degrees here, this diagram was drawn incorrectly. Because it bounced along here, we thought it was going to bounce up like this and bounce like this. What has actually happened, I'm going to draw it over the top. It's bounced along like this, it's then bounced like this, and it's now going to bounce like this instead.
Yeah.
Because this angle here is the 111.7, so we're actually interested in this angle. So it's now doing a weird kind of bounce. It's actually coming in at 68.28 degrees. So if I'm going to do this now, it's now coming along like this, it's coming along like this, and that is our 68.28, which I should probably store in the calculator. Where are you going to store that as B? I'm going to restore that in as B. So that's become our angle B. And we know that it's got the V is this thing that's here, which is 0. Let's just call that, why don't we just call it A, actually, because that's what we've said it is. So we can say that that is going to be A.
Oh,
So
a V, not a B.
so this one running along here would be A cos of B, that angle that we've called B. And going here would be A sine B. So as we go across here, this will remain as A cos B, and this one would be
0.4 A sine B.
good 0.4
E is 0.4.
A sine B. Remembering that this is our value of B, and this is our value of A. We've changed this value of B now. So we're nearly there. To find out, we'll answer the question afterwards. We've gone all the way to the end. Work out the speed and direction of the motion of the speed after the second collision. So I now need to find out what this is, which I can call W. So we know that W will be the square root of A squared cos squared B plus 0.4 squared A squared sine squared B. Putting that all into the calculator. Yep. What did you get?
How do you know?
0.49797, which is 0. I'm going to just go for 2 significant figures here, just in case there was ever any rounding, which we know there isn't. 0.5 meters per second, and that is to 2 significant figures. Then last of all, and I'll answer your question in just a second, the angle that we have here, which we can now call, we've done alpha, so let's do beta. So beta is the inverse tan of that one over that one. So that's 0.4 A sine beta over A cos beta. Sorry, cos B, not beta. Goodness gracious.
67.845.
Really? I've got something different. I got 45 degrees, which is what it is. I think you might have just typed something in wrong. You get 45.1 degrees to 3 significant figures. So we need to actually answer the question.
Exactly 45 degrees.
45.1 degrees. 45.1 degrees to 3 significant figures. So part A said, what is the speed and direction and motion of the sphere after the first collision? So for part A, we should say that the speed is 0.95 meters per second to 2 significant figures, and the direction is 8.3 3 degrees, 2 significant figures,
Oh, there's one.
to the first wall. And then part B, the speed is 0.50 meters per second to 2 significant figures. And the direction is 45.1 degrees. Or let's just do it to 2 significant figures so that everything is the same. 45 degrees, 2 significant figures to the second wall. And we could say,
Towards the
and towards the wall's intersection. Ibrahim, what was your question?
I just don't understand how you know that collision has to come here. Like,
So we didn't know that to begin with, but I didn't draw my diagram very well really, because if it's coming in at 20 degrees, it's always going to be a slightly lower angle. I've done mine bouncing up way too high here. Because we worked out that this one here was 8 degrees, and this one is 60 degrees, then the angle at the top was 111, which is an obtuse angle. So the way I'd drawn it in this diagram up here to begin with, the blue angle, if it's bouncing upwards, the blue angle must be acute. If the blue angle is obtuse, it would be like this and it would bounce inwards. So it might be worth just spending a little bit of time drawing. I might draw a couple of diagrams and see how that is. In fact, I can just draw a couple of them. Like, if you have some walls that look like this, if something is going to bounce in, like this angle, it's probably going to bounce like that. But if you had something that was bouncing at a shallower angle like this, it might bounce like this, then it might bounce like this, which means it's then going to bounce like this. So the bounces will depend on what angles you calculate. In this one, the bouncing angle here is acute. So I'm going to write that that one is acute, which means it bounces in that direction. In this one, the angle here that we calculated was obtuse, so it meant it was bouncing off in this direction. If it's obtuse, you need to use this angle over here so that you have an acute angle. It'll make more sense maybe when we do some practice on these ones as well. Hamza?
See the W, is that line go down?
The W?
Yeah, the final speed.
Yeah.
In the previous one.
Yeah, so this one is like U, V, W. This one is U, V, W. And we've got, it's all about whether it's acute or obtuse and drawing that diagram and thinking, did it make sense? Because when we looked at that one, 111.7, you saw me draw that on there and be like, what? This doesn't make sense from the way I've drawn my diagram, which means we've drawn the diagram wrong. And it actually bounces inwards towards the intersection. Okay, so we're going to do exercise 5B. We've already done questions 1 to 4, so we'll start off doing the questions from there, the odd questions 5 onwards.